Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is fabric tensile structures in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in the Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I'll certainly send you a follow-up email afterwards. So I want to quickly go over the content that we'll be covering over the next hour today. The first will be a simple example with a single cable element, and I want to explain the details of the form-finding workflow. So this is a bit different than what we saw in RFEM 5, so we'll just start off with this simple example. Then we'll move on to our second example, and this will be a little bit more comprehensive. We can see the structure over here on the right-hand side. This will include those fabric membranes as well as the cable elements, and we'll perform the form-finding workflow here as well. I'll also show you how to apply loads to the structure, including the wind load generation utilizing our standalone program, RWIND 2. So this will utilize a CFD analysis or computational fluid dynamics to place our structure in a numerical wind tunnel for the wind analysis. We will run the supporting structure design utilizing the steel design add-on. So a big benefit of RFEM is not only to do the form finding process, but also to design the supporting structure according to the various materials, including steel today, using the AISC standard. And of course, throughout these examples, we will be running the calculation and we'll review the analysis and design results. To explain the improved RFEM 6 form finding features quickly, previously in RFEM 5, the form finding loads were really a function or a property of the element itself. So meaning under the surface or the member definition type, we would also apply these form finding pre-stress loads. Well, in RFEM 6, we revamped this. So now it's defined as a load within a load case. So we thought this made a little bit more sense with the workflow. And additionally, what we can do is to define this form finding load case as an initial condition for other load cases. So we're talking about live load, wind load, snow load, and load combinations, where we combine all of these load cases into the various combinations. We also now have the ability to define multiple form finding scenarios in one model. So again, previously in RFEM 5, we really only had one opportunity to define the form finding shape. And in RFEM 6, we'll notice in this first example how we have the ability to set up different shapes. So if we kind of want to play around with the pre-stresses and explore the structure a bit further based on different pre-stress forces, then we can do so all within the same model now. We have expanded and added additional cable form finding member load options for both the geometric and force definition types. We'll see this with example 1. And finally, we have improved the surface form finding projection calculation methods. This would be for more conical type structures, like what we'll be seeing in our second example today over here on the right-hand side for both the orthogonal and radial methods. So we'll begin in RFEM, and you can see that when we launch a new model here, we'll give it a model name. The type of model is set to 3D. And under the second tab is where we can activate the various add-ons. And today we'll be utilizing the form finding add-on, in addition, of course, to the main program, RFEM 6. Now, the standards tab will be irrelevant. I'm going to manually generate my load combinations for this first example, but you can see here the default is set to the AISC 7. So within the main program, we can see our drawing grid, and currently I have my drawing grid points set up to a 1-foot increment. We can go ahead and adjust that with the right click of the grid option down at the bottom. We'll begin by drawing a new member, and the member type is going to be set to cable. So cables are a bit special in the sense that they can only take tension forces within the program. And the program will automatically also recognize that for these nonlinear elements, we do need to run a third order analysis. So that will automatically be set in the load cases and combinations. We'll see this in just a few minutes, but we know that the stiffness of the cable elements will be modified depending on what our tension forces are, requiring a third order large deformation analysis. Under the section tab, this is where I will create a new cross-section from my cross-section library, and we have two options for cables. The first is just to simply choose a round bar parametric section where we can input in the diameter manually. The alternative option is to choose this standardized section, and we can use our filters over on the left to filter to the United States. And you can see that we have several cross sections where the diameter is already defined for us, including the 1/2 inch diameter section shown here. Now I need to create my material for my cable. So I will launch my material database, and we actually will use our filters over on the left to filter to metal. And under the material subtype, we have here cable. So we only have a few options available under this material definition type for cables, and most likely the material that you're going to be using from your selected manufacturer is not shown here. So we want to take advantage of a user-defined material. So what I would suggest doing is to utilize one of these materials that's already available here simply as a template option. So we can choose the manufacturer Pifer, for example. I click OK, and then I'm immediately going to go into the edit material settings. So within the edit material settings, this will allow me to turn on the user defined material here. I can even give this a new name, whatever it may be. For this example, we'll call it user defined cable material. Under the second tab here, material values, this would be the information that we receive directly from the manufacturer for our particular cable element that we're using. So I'd want to go ahead and modify those material properties. Once we're done doing this and we click OK, we should see that material update automatically here within the same dialog box. Now, if you have multiple user-defined materials for our cables and we don't want to constantly re-enter these into the program for every new model, what I would suggest working with is what's called templates. So we'll get back to drawing this member in just a minute, but once you've set up your user-defined materials, maybe common cross-sections that you're using for all of your RFEM models, and possibly even the load cases and combinations, we can go up here to File, Save as Template. And then when we create a new RFEM model back in this dialog box that we initially saw, you can see that template is an option here where we can select one of the saved templates that we've created. Notice I have one called cables here where maybe I have all of my materials already set up for my user-defined cables. So getting back to drawing this member, remember we want to set the member type to cable. We've already defined the cross section. I'm going to snap to a point here at 0, 0, 0, and my second point will be at 30, 0, 0. So a 30-foot long cable. Now we do need to support this member, so we'll apply a new nodal support. We'll just go ahead and take advantage of the default hinged option shown here. I click OK, and then I just simply highlight over the two nodes on either end. So by default in our load cases, automatically the self-weight load case is generated, and we can modify this name further and give it an abbreviation of SW. Self-weight is active here. We have set the action category automatically to dead load. So when we click calculate, what we should imagine here is some downward deflection of this cable element. And we see here a downward deflection in our navigator results of 2.3 inches. We also can view the internal forces such as the tension force, which will be around 0.4 kips. So the very premise of form finding is to add in these pre-stress loads before we take into consideration any additional static loads. Maybe we want to decrease these tension forces altogether. So what I want to do is to go back into my load cases and create a new load case definition. The name will be called pre-stress with the abbreviation of P. Notice self-weight is unchecked here. The action category for my form finding pre-stress loads must be set to the self-straining force. So we have developed the program so that the form finding will take place under this action category only. So we want to make sure that this is set here according to self-straining force. I click OK. I'm back in RFEM and this is currently just an empty load case. So we will define here a new member load. Well, now instead of the load type being set to force, we use our dropdown and we can select form finding. So this particular load type is available because I've activated that form finding add-on at the beginning of the example. And we have two definition types, either geometric, which we can see within our dropdown where we can specify the pre-stress length, the unstressed length, or the sag. Alternatively, we can define the force and we use our drop-down box here and we can see we can define the average force in the member, the maximum force, the minimum force, and many other options. So we've really expanded on this within RFEM 6. So for today, we are just going to choose the geometric option with a defined sag. And I want to specify a sag here of 8 inches or 0.67 feet. I will apply this to member number 1. I click OK, and now we see graphically this pre-stress load applied to our cable element. So I would imagine that when I run this calculation here, I should see something of the sort of an 8-inch sag applied. But in fact, when we run the calculation and we're currently looking at the global deformations, everything is set to 0. I can even look at my member internal forces and I have no tension forces either. So what exactly is the issue here? Well, we've defined this sag, but the program has absolutely no idea in which direction to apply the sag orientation. Should it be up? Should it be down? Left, right? So the reason for this is because we have no other guidance or loads defined with this pre-stress option here. Well, we can fix this by possibly considering just the self-weight during the form finding load process. So I go back to my load cases, and what I'm going to do is to create, or actually it's back up a step under the base tab. Let's uncheck the combination wizard. So I'm going to manually create my load combinations instead. So I go to my load combinations tab and we'll create our first load combination, but I'm going to give it the user defined name here of shape 1, which is going to be equal to my self weight plus that pre-stress load. Well, we can see here it's set to large deformation analysis. Again, the program recognizes these cable elements. And under the assignment tab, we will move both self weight and pre-stress over to the right, assigned to load combination 1. So now when I click the calculate button, what we should see are hopefully some results. And sure enough, if we take a look at the global deformation, I now see a deflection of 8.47 inches. So this is better than 0, but it's still a little bit more than that 8-inch sag that I initially defined. Well, this is really just an issue of accuracy. And we can increase the accuracy by increasing the number of iterations during the form finding process. So I'll go back up to my load combination that I just created, and under the static analysis settings, I'm going to go into the edit options here. And we also have a tab for form finding. And notice the default number of iterations is set to 15. Well, I'm going to increase this and set it to 50 instead. So I click OK. I'm going to rerun that calculation quickly. And now what we'll see under our deflection is 8.04 inches. So we're quite a bit closer to that 8-inch sag than what we saw just simply by increasing the number of iterations. Maybe we're also interested here in the member internal forces, the tension force. So we can see now this is decreased significantly to 0.114 kips in comparison to just running the self weight. All right, so I had mentioned in the PowerPoint that within RFEM 6, we have the ability to kind of play around with the different form finding settings and to see the different shapes or form finding shapes on the structure all within one model. So let us go back to our load cases tab, and I'm going to define a new load case here. And this is going to be called dead load with the abbreviation of D. The action category will be set to dead load. Notice self weight is unchecked here. I go back into RFEM and we just simply have an empty load case. So I'm going to apply a new member load. The load type will be set to force, but it will be a concentrated load with a load magnitude of negative 2.25 kips. And I'm going to apply it at 50% of the member length, and I specify member number 1. I click OK, and we just see this simple point load applied right here at the midspan under load case 3. Well, I now want to combine this dead load case with my form finding conditions. So I'm going to create yet again a new load combination. And I define a new load combination here. I give it the user defined name of shape 2. This time though, it's going to be equal to my dead load that I just created, that point load, plus my pre-stress conditions. And under the assignment, we can move over the pre-stress load as well as that new dead load. I am not going to consider self-weight for this particular shape. So I click calculate, and what we'll see here after the calculation is done is we take a look at our deflection, and sure enough, we'll go ahead and turn off our grid and our applied load here. We have a deflection that is still close to that 8-inch sag, so 8.04 inches. But notice how my deflected shape looks quite a bit different, more of a triangular distribution here. And by the way, you can always adjust the deformation factors here over in the control panel to something larger or smaller. We can take a look at our member internal forces, and we see here we now have a tension force of 25.2 kips. So this is how, again, we can kind of explore these different form finding settings all within the same model. What else might be interesting to us is if we go under the navigator display options, and all the way at the top, we have this option here for display topology. And the initial option is to show the original shape. So this is before the form finding has taken place. And notice our results are presented to us still just on this completely straight cable. Alternatively, we can view the deformed shape, and our results and our tension force is displayed with that triangular distribution shown here for that deflection. Going back into the load cases, what else I want to point out is that we now have the ability to very easily add load factors during the form finding process. So if I take a copy of shape 1 here, and I'm going to rename this one to shape 3, I'm going to apply a load factor, and I'll just simply rename this one to begin with, of 1.6 to the self weight. Well, under the assignment tab, you can see that currently these factors are set to 1.0. So if I want to adjust this, I can just simply type in 1.6 with my factor here, and we can rerun this calculation. Now, what we would expect is to see similar deflections. Yet again, we're still reaching that 8-inch sag that I have previously defined under form finding. But if I take a look at my tension force, this should be slightly higher now that we have increased that load factor for my self weight. So you can see it's 0.183 kips. If we take a step back and look at shape 1, you can see the tension force decreases to 0.114. All right, so now we have explored some of the different scenarios with this initial form finding shape, but how do we combine this now with additional load cases like live load, snow load, wind load? So we will yet again create one more load case here, and we will call this one live load with the abbreviation L. The action category is going to be set to live. I go back into RFEM and I need to add a new load here. So I will go to a new member load. The load type will be force. The load magnitude will be negative 0.33 kips per foot applied to member number 1. I click OK, and now we see this load applied to our cable element. Now I can always right click here and use this slider to decrease the size of the load on the model. So now that we have created the live load, we need to combine this with that pre-stress form finding initial shape. So I'll go to my load combinations, and I'm going to create my first load combination that has more to do with the static analysis rather than the form finding shape. And with this load combination, I'll give it the user defined name of self weight plus the live load. But before I can run the static analysis, I need to tell the program which shape to start with before I apply these additional loads to the cable. So I'm going to turn on this option here to consider the initial state from the shape 1 available under load combination 1. So now the program will be intelligent enough to first run this form finding condition, then it will move on, and we can see under the assignment tab here, to apply both self-weight and that live load. So I can run the calculate button, and what we should see once the program is done solving here, we take a look at the deflections. We'll turn off our loads. We can see a deflection here of 19.36 inches. We can take a look at our tension forces, 23.15 kips. And what else might be interesting to us is the topology options that I previously showed to you are also available here under the drop-down box within our toolbar. So we can view the results here on the original shape. Again, this is before the form finding has taken place. The next available option is the initial state shape. So this is after the form finding has taken place. And finally, we have our third option here for the deform shape. So now we have applied self-weight and live load for the static analysis to go ahead and do our design of this cable structure. It must be pointed out too that we can create multiple load combinations. We can change out these different shapes here again to do further research into how our structure is going to be affected based on the different form finding settings. So that will be all for the first example today. Really relevant to cable structures here, basic form finding workflow. But let us move on to our second example. So I have already modeled here our supporting structure with our steel pipe members, and I will go ahead and explain here under the base data initially what I've also set. So under the add-ons, of course, we're going to activate this form finding add-on. But notice too that I've also activated the steel design because I'm going to utilize the steel design add-on to also design this supporting structure according to the AISC. And I've activated here wind simulation. So this will take advantage of our standalone program, RWIND, for that CFD analysis or that numerical wind tunnel. Under the standards tab, I will generate my load combinations automatically according to the AISC 7. My standard group for my load wizard, so this is related to my wind load profile that I'll be utilizing for our wind. This will make a little bit more sense later on. And steel design, you can see here from my drop-down options, I have this set to the AISC 360. One more thing to point out under the model parameters is I have went ahead and linked this to our GeoZone tool. And this is available under the DeLuval website, where we have integrated all of the various standards here, including the AISC 7 for the various hazard loads. And this is linked up to Google Maps technology so that what we can simply do is to type in a location. So let's say our project is located in Philadelphia. The program or the GeoZone tool will automatically update here to give me my basic wind speed. This comes again directly from the AISC 7. You can see I have it set to risk category 1. So once we have set our project location, all of that information is brought into this model that will just assist us with some of our automatic loading for wind, for example. So as mentioned, I took the liberty here to model these steel members. We have plenty of other webinars that show the workflow for modeling steel members and running a much more detailed AISC steel design that you can refer to on our website. But what I did not do is model the cable and fabric membranes because I do want to show the workflow for this. So what we'll begin with is the new cable member. So I go up here to draw a new member and the member type is set to cable. We saw this with example number 1. The section is going to be set to a 1/4 inch diameter with my user defined cable material. So once I have this information set, I can simply click to the point locations here of each of my cantilevers. So notice I'm just snapping from one point to the other. Now, these cables are going to be used to define the boundary, the bottom boundary of my fabric membranes. So once we are complete here with defining each of these cable elements, we can see them modeled at the base here of what will be our fabric membranes. So to begin with the fabric membranes, I want to draw a new line element. And a line element has no member properties. It's exactly as it sounds. It's just a simple line. And it's going to be used to further define the boundary lines here of my first fabric surface. So I'm just snapping from the top of the model down to the bottom, and I right-click a couple times to exit out of this option. To create a new fabric membrane, we need to generate a surface. And the problem with these surface options available here is that these must all be in one plane if we use the surface options available. The problem is that up at the top, we have this curvature. So the surface will not be in one plane. Rather, we want to use what's called a quadrangle surface. And you'll notice a quadrangle allows us to have some curvature defined. The stiffness type is going to be set to membrane. And a membrane is special just like a cable element in the sense that it can only take those in-plane forces or those tension forces. We need to define a new thickness and material for our fabric membrane. So I define a new thickness type here. I will immediately define a new material. And once again, similar to our cable elements, we'll use our filters over on the left to filter to fabric. And we really only have two options here. And again, 99% of the time, you probably are not going to be using these fabric materials for your structure, but you're going to be using your own defined fabric from the manufacturer. So we're only going to use the available materials here, once again, as a template. So I just go ahead and select any one of these materials. I click OK, and I immediately go into the Edit Material settings. Again, similar to the cable element, I want to turn on the user-defined material, and I'm going to give it a user-defined name here that I would use for my fabric material. Under the second tab is where we can input in information that was given to us directly from the manufacturer, such as the modulus of elasticity and the local X and the local Y directions, shear modulus, Poisson's ratio, and so on. And all of this information is used to calculate the global stiffness matrix of the membrane itself. Once we input this information, we will see under the Material Values tab here, the basic properties will be calculated automatically. Now, the one thing that we do need to also set, though, is the reference thickness. So whatever our thickness is of our membrane that we got from the manufacturer, we would go ahead and input that in here. And for our case today, we will use the thickness of 0.039 inches. So going back to the main tab, I can go ahead and click OK, and we should see that material update. The thickness is automatically updated here as well. So once I click OK, and I click OK once again, I can just simply select the boundary lines of this first surface element. I'll turn this into a rendered view, and we see the surface generated. I will select the surface, and I'm going to use my Rotate Copy tool. I'm going to create 3 copies with a rotation angle of -60 degrees, and I can use the rotation point of 0, 0, 0, or I can modify it as well with this arrow option. So now we have the initial surfaces generated on the left-hand side of the structure. So as far as the surfaces in the center, it's a little bit more complex. So we need to continue defining these boundary lines. So what I'm going to do is to take this node at the center. I'm going to use the Move Copy tool to create one copy, and I'm going to move it 1 foot up in the vertical Z direction. So we just see that node copied there. I'm going to define here a new line element, but the line type is going to be set to arc. The object snap settings within the program allow me to detect here the center point of this front cable. My second point will be the top of that copy node, and my third point will be the center point of that rear cable. I can right click to exit out of this dialog box, and now we have this arc element shown here. I'm going to also utilize this Divide Selected Lines tool. What this allows me to do is to highlight over this entire middle section here, and it will break apart these lines and these members where we have the intersecting nodes. Finally, I'll draw my last line element by drawing a new line here. A single line is fine. I snap up to the top of my structure and snap down to the top of that arc element. I'll right-click to exit, and we can continue defining the quadrangles here at the front and rear of the structure by drawing a new quadrangle surface. Remember, the stiffness type must be set to membrane. I don't need to redefine the thickness or the material. And by the way, if you have these user-defined materials for your fabrics as well as your cables, remember those template options to go ahead and save so that you can open up an RFEM model with those user-defined materials already set. We click OK in this dialog box, and then I can simply select the boundary lines here for my quadrangle that will be located at the back of the structure. I will do the same thing at the front of the structure, selecting my boundary lines, and we can see those quadrangles generated here. So the surfaces are complete on the left side. And one thing I want to point out is by right-clicking and under the option to display the local axis systems of the surfaces, we can see them shown graphically here. I'll turn this to wireframe view, and you'll notice the local axes are kind of oriented in every which way. And this is a problem for many reasons. Number one, if you remember, our material input, such as the modulus of elasticity, is based on these local X and Y axes. Also, our form finding settings, when we define those pre-stress forces, they're also going to be based on the X and Y directions. And finally, our results are all based on local axes of the surfaces. So if everything is going in every which way, realistically, our results are not going to be correct. So we need to align these so that they have a nice orientation all in the same direction. So I'm going to highlight all of my surfaces by holding down my control key, but I'm going to deselect this surface here at the front right with my shift, and I'm going to right click on these surfaces, and under the surface option, we can reverse the local axis system. And I'm actually going to right click on this back surface here, and I'm going to reverse the local axis system here. So now all of these Z axes are pointed inward. But I want to take this a step further by selecting all of my surfaces, once again by holding down my control key. I'm going to double click to edit them, and under the specific axes checkbox here, we now have an input axes option. And I use this drop down to select the axes directed to a point where I can choose to orient all X axes towards the point that I can select graphically. So I'm going to choose the option here to graphically select the bottom center of my structure up to the top center. You can see the coordinates are automatically populated. I click OK, and now we should see all of the local X axes oriented right towards the center of this conical shape on the left-hand side. So I'll highlight all of these surfaces once again, and I'm going to utilize my mirror tool. A mirror tool is exactly what we would see in something like AutoCAD, where we can create a copy. We can mirror about the YZ plane, and then I graphically choose my mirroring point, let's say the top of that arc element. I click OK, and we should see all of our surfaces mirrored to the other side. But of course, we have a problem here with our local axes. So I'm going to right click, and under the surface option, I am going to reverse the local axes so that now all my Z axes are pointed inward. But if I double click on these surfaces, under the input axes, all the X axes are still pointing to the left-hand side of the structure. So let's just update that to the right-hand side instead. So I choose the bottom center point and the top center point. I click OK, and now we should see the orientation of those local X-axes all pointed upward toward the center on the right-hand side. So everything looks good there. So now our modeling is essentially complete here with the fabric membranes and the cable elements. We want to move on to the pre-stress forces for the form finding workflow. So I will begin by creating a new load case, just like what we saw with example number 1. I'll create a new load case with the name pre-stress. The action category, as I mentioned, must be set to the self-straining force. I click OK. I'm back in RFEM in this empty load case. So we want to first apply our pre-stress loading conditions to our cable elements. So I'll utilize my Navigator Views tab here to turn on only the elements with a cable material. Notice everything else is grayed out except for these cable elements down at the bottom. So while we're under this pre-stress load case, I create a new member load definition, and we're going to choose, of course, the option form finding, and I'll take advantage of the sag option once again, and I'm going to define a sag here of 6 inches or 0.5 feet. And once I click OK, I can highlight over all of these members. I click OK, I cancel out of this visibility, and we can see the sag applied all the way around the structure for each one of these cable elements. So we want to move on to applying the form finding conditions to our surfaces. In a similar manner, we are going to define a new surface load, and we're going to choose the load type form finding here as well. So we have two calculation methods here. We have the standard, which you can see updated with the picture over on the right-hand side. The standard is really for more flat type membranes that we'll be utilizing for our structures. And underneath the hood for this calculation method, this will indicate a vector that can move freely in space until it reaches the target position. Now, alternatively, we have the projection option here. And you can see that this might be used for more conical type structures, such as what we have today. And this will indicate a vector that can move partially in space, but it's fixed in its X and Y coordinates as well. So under the load distribution, we have either here an orthogonal load distribution, or in our case today, we'll be utilizing the radial load distribution. So what we'll need to specify then is the pre-stress load here of 0.05 kips per foot in both directions. Then I need to specify the two center points of this conical structure. So we start off, once again, similar to our axes on the left side of the structure by snapping to a point at the bottom and snapping to the point up at the top. I will graphically highlight all of these surfaces, so surfaces 1 through 6. Now notice I just hit apply and next because I'm still within this same dialog box, but my loads have been applied in the background here, which we can see indicated by these symbols. Well, I'm still within this same dialog box because what I want to do now is to modify my center points to the right-hand side of the structure. And the coordinates update automatically, but this time I want to graphically select my surfaces on the right-hand side, surfaces 7 through 12. I click OK through these dialog boxes, and we should now see our pre-stress form finding loading conditions. So what I'd like to do now is to run the calculation, but we might be thinking, well, based on example 1, if I run this calculation, I probably won't see any results because I didn't include something like self-weight within this load case. But that's actually not true. So yes, we have defined a sag around the exterior here, but we've also defined these additional loads on the membranes. So now the program has the intelligence here to search for that form finding shape and apply the sag based on the additional loads from the fabric membrane. So it has some guidance there that we don't necessarily need to consider self-weight in this particular load case. If we go to calculate mesh settings, before I run this calculation as well, notice the target length of the finite element mesh is set at 0.75. Maybe we want to alter that for our initial form finding pre-stress case. So the program will go ahead and generate the mesh here, and it will run through the various form finding load conditions until we see our deflected shape here. And everything looks quite nice, again, just based only on the form finding itself. So let us run through exactly what our results are showing us. So we see here the global deformations, and we can view this all around the structure for both the surfaces as well as all of our membrane, or as well as all of our cable elements as well. Under the members option, we're probably very interested in the cable internal forces here. So we activate member internal forces. Maybe I take a step back and I'm going to deactivate the A53 grade B material, but I'm going to activate only my cable materials. So now I'm just viewing the internal forces here for each one of my cable elements just based on this pre-stress condition. We'll cancel out of this visibility, go back to our Navigator Results tab, And in addition to the member internal forces, let us take a look at the internal forces for our surfaces. So we see here the axial forces NX and NY. And again, these are based on the local axes of the elements themselves. So we see here in kips per feet, in which the center of the structure, we're pretty close to that 0.05 kip per foot input that I put in for the form finding conditions. As we vary around the structure, especially at these steeper inclinations, it might vary a bit. Same concept for NY. What else is applicable here during the form finding is the shape tree options. So for example, I can activate the contour line. So currently I'm viewing the contours just based on inches here. I can activate the inclination, which is showing me based on degrees. And also I can activate the inclination directions. And under this second tab here in my control panel, notice this red arrow points me to which factor I can currently control. Maybe I decrease this factor. And now we can see with these line elements exactly where the inclination direction is for that form finding case. Okay, so realistically, that is the pre-stress form finding workflow. But now that we have went ahead and solved for this condition, we need to consider the additional load cases for our static design. And what I'm talking about is concepts like live load and wind load. So we go to our load cases tab and we'll create a new load case here with the load case name live. The action category must also be set to live. Notice self-weight is unchecked here. So what I can do is to click OK. I'm in this empty load case here back in RFEM. We will apply a new surface load. And the load type is going to be a standard force with the load magnitude here of 0.005 kips per square feet. But notice I'm going to apply this based on the local coordinate system here, the local Z direction of my surfaces. So when I click OK and I highlight over all of these elements, we can see here the live load applied to all of those fabric membranes. Back under my load cases tab, keep in mind though that if we want to look at these load cases and run the calculation for both self-weight and live load, we want to make sure that we turn on the initial state from the pre-stress load conditions here from form finding. So the program will then run through the initial state here for the pre-stress. Remember, we've already run through this, what the initial starting condition should look like before moving on to the static loads such as self-weight and live load. We do want to create one additional load case here, and this one is going to be wind with the action category set to wind load. Again, we'll also set the initial condition to pre-stress, but this one is going to be a bit special. We're already familiar now with how to apply basic surface loads, member loads, but remember, I activated the wind simulation in the base data. So this is going to utilize the standalone program RWIND for that CFD analysis. When we activate this analysis type, we have a couple additional tabs here. And because of the sake of time, I really don't have the ability to go into much detail for all these wind analysis settings. We have additional webinars and online resources on our website that will go much more into detail with our wind in itself. But you can see here the wind analysis settings are controlled within this dialog box. For example, I've decreased the finite volume mesh to 10% just for a quicker calculation, less accurate though. The steady flow, I increased the number of iterations to 600 and several other settings within here. The wind profile, if you also remember under the base data, I said we're going to generate the wind profile according to the AISC 7. So we can always modify the standard back under the base data, but for now, utilizing the AISC 7, what we see here is that the program has brought in that basic wind speed because I have linked that to that online GeoZone tool available on the DeLuval website. Well, I can make further changes here, such as exposure category, maybe some of my coefficients, and ultimately this information goes into calculating the wind load profile here as a function of height. So this will be used with the wind analysis in RWIND. we want to orient the structure here 90 degrees around the z-axis. So this is just going to rotate the structure in my wind tunnel. I'll show you this in just a minute. So realistically, we could run our wind simulation under the hood. We don't even need to open it up within the program. But what I did want to show you is just a brief example here of our wind simulation and showing our structure here within the program. So you can see that the RFEM model was automatically brought in to this standalone program. And I'm going to go ahead and start the calculation now while I continue to talk about what exactly is going on here. So notice the initial form finding shape is also brought in here because I've solved for that. I set that as a prerequisite here before we consider the wind analysis. And if I jump back to this model tab, we can see our numerical wind tunnel. And I've rotated this 90 degrees because I wanted the wind to be oriented here based on my structure within the wind tunnel shown. We see the wind will be applied from the left to the right based on this red arrow. The wind velocity at the start is based on the AISC 7 wind load profile. And by the way, you can always create your own wind load profile too if it doesn't fit within the standard. We have a mesh within this numerical wind tunnel. You can see it becomes more refined as we get closer to the structure. Under the zones tab, we're going to shrink wrap a mesh around the structure so that we can use this to calculate those wind loads within this numerical wind tunnel. It's wrapped around each individual member. So very, very accurate here. So ultimately, when the calculation is complete, you can see here the progress bar under our simulation settings. What we'll be presented with is our wind pressures directly on the structure. So the program will give us a message here that will say, okay, the calculation's complete. Do you want to go back into RFEM? Let's go ahead and click no for right now. We can see the wind load pressure shown directly on the structure, and I can move my mouse around. I can rotate the structure to see some of those uplift forces. I also want to preface that these wind pressures are taken directly back into RFEM, and they're applied to every single FE mesh element within RFEM so that it can be used for the static analysis. Now, additionally, if we're interested not only in the pressure on the structure, we can view the pressures around the structure as well. And you'll notice I can use this slider option here to view those pressures within the wind tunnel. I can view velocities as well. So the wind velocity is shown here. We also can take a look at the velocity vectors. So we can see the direction, the magnitude of those wind loads moving around the structure. And finally, we can display the streamlines. So again, the wind moving from left to right here, we can turn on our flow animation and we can see exactly how the wind is moving over this structure. We can save these videos, export them out, add pictures to our RFEM printout report. And we might be thinking, well, why would we want to use this standalone program? And I think it's pretty clear to say that these unique fabric structures really have the geometry that doesn't necessarily fit into the minimum wind load standards, such as the AISC 7. So we want to use this as an additional tool here just to get an idea of what our wind loads on our structure can be. So once we are done running the RWIND calculation, we just simply exit out of here. And again, all of these results will be brought back into RFEM. So now that we are done defining these various load cases, we need to combine them into the load combination. So back under the base tab, notice I have activated here my combination wizard according to the AISC 7. The actions tab, I am going to deactivate here this self-straining force. I do not need the program to consider it further in my combined load combinations. Rather, we are always going to use this particular action category as a initial condition. So we do so here under the design situations. And the design situations are really needed for our steel design. And you can see here my LRFD design situation is generated as well as my ASD design situation. And what we want to do here is to go into the detail settings, and similar to what we did with our load cases, we want to activate the initial state from the pre-stress load case number 2. I click OK. Now this same combination wizard is used for both my factored and my unfactored load combinations. And I jump to my load combinations here and I can see my factored load combinations listed individually in orange, my unfactored load combinations listed in red, and every single one of these has the initial state from load case 2 for my pre-stress. So the program will apply the form finding conditions before it moves on to the static analysis with dead, live, and wind load. And of course, we can control this individually here for each load combination, but by setting it under the design situations, it automatically imported in this initial state here. Okay, so we're finally ready to run the analysis, but one thing that I wanted to point out is the entire benefit of RFEM 6 now is these add-ons being integrated directly within the main program, including for steel design. So again, I won't get too much into steel design. Obviously, we're ending the presentation today for the 1 hour, but just to touch on this, for our steel design today, I'm going to design these 2 columns. So I will highlight them here. And under the Design Types tab, I need to define a new effective length for these members. So I can go in here to define a new effective length. And for these pipe elements, I'm not concerned with torsional buckling or lateral torsional buckling, only flexural buckling. And it's within the effective lengths that we define the information for unbraced lengths. Incredibly important for the design. It does not affect the analysis at all, but we know that unbraced lengths are needed for the design according to the AISC. So I can immediately override this here for both my strong and weak axes to maybe something more like 13 feet instead of the full member length here. So I click OK, and now we have that effective length set for our 2 pipe elements. Now I want to run the same workflow for all of my cantilever elements, but you'll notice I have also selected my cable elements. Let's go ahead and go back to our Views tab to deactivate the cable material, but rather only activate our steel material. I will yet again select all of these cantilever members. I can double click to edit them. And under the design types, we want to specify a new effective length, deactivating torsional buckling, lateral torsional buckling. And I simply want to override the unbraced length here to 5 feet for all of these cantilever members rather than the full 10-foot length. I click OK, I click OK. And the final step before we run the calculation is to jump down here to my table, and I'm going to choose the Steel Design add-on. Notice we have here under our design situations our LRFD design situation. Remember, that's the factor load combinations. And we have AISC for unfactored load combinations. So I simply want to relate the LRFD factored load combinations to my strength limit state according to LRFD design. But my unfactored load combinations, I'll relate this to my serviceability limit state design. Now my objects to design, what we can do is just to select the relevant objects here. Maybe I only want to select my pipe elements as well as the cantilever members, because those are the only 2 that I've defined those unbraced lengths. Otherwise, the program will give me an error. You can see, let me check that one more time. Okay, looks to be selected here. Okay, so now that we have defined all of this information, we can finally go to calculate, calculate all. The program has already run through this initial form finding condition. It's going to use that as the starting shape now for all the rest of my load cases and combinations. You can see they're going to solve very quickly now in RFEM 6, our steel design solves, and we are now presented with our results here in RFEM. So we're currently looking at the static analysis. We can see this in our navigator results dropdown here. Now we've already visited some of this information, topics like global deformations, and we can change around to our different load cases here. But we're also interested in our member internal forces. So yes, we can view the axial forces or the tension forces within our cable elements, but maybe we're also interested in information such as MY, our moment for our strong axis, our weak axis. And for any one of these members too, we can always right click to go to what's called the results diagram. This is just going to allow me to turn on these internal forces for any one of the members to see what's going on in a little bit more detail. I can even scroll to the different load combinations here. I can add this information to my printout report. I can move this over to my second monitor and continue working concurrently in the program, and everything will update in real time. Now we're also interested in our axial forces for our surfaces. So what we can do here is to view the initial state or the deformed state, doesn't matter. We can view the NX forces based on our color panel here. We can view the NY forces. This is what we would want to compare, of course, to our manufacturer's limits. Now, graphical view of these internal forces is nice, but maybe not so helpful in terms of really sorting through the information. So all of this is available in table format, where we can view, for example, the results by the surface. And we can jump down here to the basic internal forces. And notice the program syncs up in the background exactly which surface we're looking at here. We can see, rotate this around, that red arrow is showing me exactly where the controlling internal force is. Now there's a lot of zeros in this table, and that's just simply because, remember, those membranes can't take moments, they can't take shear forces, only axial forces. So we can always go to our filter options here and turn off moments, turn off shear forces. And now we should see this table that's only showing the relevant axial forces. And of course, if you remember, we also ran the steel design. Again, just a brief introduction to this. We're looking at that steel design add-on where we can view the design ratios by the member. So I'll turn this to wireframe view. Notice the program automatically syncs up graphically here. It's showing me for every single member exactly the code check from the AISC. So relatively low code checks here for these particular members. And for any one of these checks, I can always go up to my design check details, and new within RFEM 6 is just a complete output here of our results, including code references, code equations, all that goes into determining this design check ratio given here. So we can add this as a graphic to our printout report. We can even change to some of the different checks here for this model, or for this particular member at this X location. Again, very, very transparent in where the numbers are coming from. Okay, so that really gives an overall introduction to the full form finding workflow, including the static analysis, the steel design. One final thing I just want to touch on is let's take a look at the printout report. So perhaps I'm interested back in the static analysis here, and I want to take a look at my NX forces for my fabric. And I'm going to modify this in the reverse Z direction here. And I'd like to print off the NX and NY forces for several of my load combinations that I've created. So I have the option, of course, to run through each one individually, add it to my printout report, but rather I'm going to show you a bit quicker option. So the first thing to do is to create a new printout report up here in our toolbar. And we can take advantage of some of the default template options, including the input data and reduced results, which is what I will utilize today. Otherwise, you can create your own template. Turn on and off whatever you see here for all the various options, save it as a template, and use this for all of your future RFEM models. So I create this printout report, kind of generates this in the background, but I'm going to next go up to the option to print the graphics to the printout report. And what we will initially see here is the NX and NY forces. And notice it's taking up the full page height here. And what typically you would also see is this color scale shown on the inside. So if we wanted to modify any of this, we can change the height, for example, to maybe only 50%. So I can input that in directly here. Maybe I want to use or move my color panel outside of here. So that's one option we can make a change to, so it's not blocking any of the graphics. But lastly, I want to take advantage of the multi-print option. And the multi-print option will activate this results tab here. And under these surfaces, this is the exact same information that I saw within the main program. I can show the internal forces NX and NY. And I can select now multiple load combinations here to print off these internal forces. So perhaps I want to choose my first 3 factored load combinations, for example. I click OK, I click Save and Show. And so now what the program is going to do is to cycle through those first 3 factored load combinations, take a quick snapshot of NX and NY. Once it's done with that, we'll also see the progress bar in the lower left-hand corner here. It's going to create the printout report. And so we'll see here a separate application for our printout report given to us. Now, it looks a little bit overwhelming, but we can always right-click to collapse all of these chapters, and now we see them individually listed here. And if we jump down to the static analysis results, and we kind of zoom in here, sure enough, here are all of my NX and NY forces for each one of those factored load combinations. And these pictures are going to update automatically. So if I make any changes to the model, then these pictures will automatically update. I can again even drag this model to the right-hand side here. Everything will update automatically. So I don't need to worry about printing off those graphics again. You'll notice up here in my cover photo, the original structure is not really showing that form finding load case being applied. So if we wanted to edit that, we could right click, choose edit. The program will take just a couple seconds here to recognize exactly which picture we need to edit. And maybe I kind of modify my rectangular shape here and I choose the option to clip the graphic to the selected rectangle. I'm going to choose a solid rendered view, but the shape of the initial state. I'll turn off my grid down here at the bottom, and now we can see that once we click OK, the program will bring back up this printout report, and we should see the cover photo updated accordingly here. And sure enough, here is that rendered view. So again, we can add our own logo to this. We can add further information, turn on and off different settings, save this as a template, and use it for multiple RFEM projects. All right, so one more thing just to mention before we conclude the presentation today, talking about future RFEM 6 development related to form finding. We are currently working on the cutting pattern add-on. So this is the flattening process to produce the cutting patterns. This will be relevant not only for tension membrane, but also pneumatic cushions within RFEM. So both are possible with the form finding capabilities and will soon be available for cutting patterns as well. Now, we did have this capability in RFEM 5, but we'll definitely see some improved technology in RFEM 6, for example, improved cutting line definition. That will be quite a bit easier than what we saw in the previous version. We'll have the ability to export out these patterns, such as a DXF file, and give them directly to the manufacturer. So something that is currently in development, and we should see available in the coming months. So this webinar will be recorded, will be placed on our website where you registered for the GoToWebinar. And the models that you saw today, you can download for free. You can open them up in the free 90-day trial version of RFEM available on our website as well. The trial version is full capability, includes all the add-ons for the full 90 days. If you have any questions about today's presentation or anything else, feel free to contact us at our Philadelphia office, and you can see the contact info available down here at the bottom of the screen. In particular, our email is info-us@deluwalk.com. So we will have many more upcoming webinars as we continue to introduce the new features of RFEM 6. You can register at deluwalk.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place. So feel free to keep an eye on for that and register directly through the email. PDH certificates will automatically be emailed to all participants. This does not happen automatically after the webinar. It will take usually about a day or so before you will see those. They will be emailed to all participants who are here for the full presentation, the full 60 minutes. This is a requirement of the states that we are pre-approved providers for PDH. So again, if you were here for the full presentation, you can expect that PDH to be delivered to your email relatively soon. If you watched with a colleague or in a conference type setting and you yourself did not register for the webinar and you are wanting PDH credit and you're also here for the full 60 minutes, please request that PDH at info-us@deluwal.com and let me know who you watched it with, and you want to take care of that relatively soon after this webinar will end. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next presentation. Thank you.